Bismillah ar-Rahman ar-Rahim. Today I will talk about very important topic, that is the nuclear spin and nuclear configuration by using the nuclear shell model and filling of the nuclear energy levels both at ground state and the excited state. And based on this knowledge, you can identify or differentiate the responsive or NMR active isotopes based on the nuclear spin. So nuclear spin is very important. So today we will explore how can we calculate the nuclear spin. So the first, there are four learning objectives, and basically the nuclear spin is actually the filling of the neutron or the protons in the energy levels. So there may be four possibilities. One is the even combination. That means when both number of protons and neutrons are even nature, then the spin will be zero. So there is another combination, odd combination, when both protons and the neutrons have the odd combination, then the spin of the nuclei will be positive integer. That means 1, 2, 3, 4, 5, 6, so on. So there is two other combination, 3 and 4, when it is the odd even combination or even odd combination. That means any of the neutron or the proton is having odd and other is having the even combination. Then all spins will be the half integral. That means half, 3 by 2, 5 by 2, 7 by 2, and so on. So these are the different types of the filling of the protons and the neutron in the energy levels. So we will explore how to calculate the nuclear spins by using these four objectives. So let's move to the second slide. I'm just going to show you this as a reference, just to remind you what we are going to do with the electronic configuration. So basically there are the four quantum numbers. One is the principal quantum number, which tells us the information about the shells. And then it is the angular quantum number, which tells us the information about the subshells. And then it is the a magnetic quantum number, which describes about the number of orbitals, and actually subshell defines the shape of the orbitals. So there is the simple way to calculate. I'm not going to go to in detail of the electronic configuration. Just I'm going to show that is in a similar way, the protons and neutrons are also occupying their energy levels, as the electrons are going to be filled up in the shells or subshells and the orbitals. So if you want to get further help, this is another link of my YouTube lecture. You can go there and then to learn about more about the different quantum numbers and the electronic configuration. So this is not our topic. This is just I'm going to show you as a reference. So this is actually the nuclear shells or the filling of the nuclear energy levels. And you just have a look on this energy levels. So these are actually not exactly the same as we have the in electronic configuration, but it is a little bit similar to the electronic configuration. So let's see what is the different information is written over here, and how can we fill up the protons and the neutrons in the energy levels. So the first is like here, this is written, this is actually the increase in energy from the 1s to the 1g. So here, if it is 1s, 1p, that means it is like a similar to the principal quantum number, and this is the angular quantum number. So actually this energy level is about, we call it the quantum energy states of potential well, including angular momentum effect. So with the angular momentum and the principal quantum number, we here we are going to build up different energy levels. So it is starting from the 1s, then 1p, then 1d, 2s, 1f, 2p, and 1g, and so on. So this is the general differentiation, what is telling us 1 and g. This is very important because this information we will be using to calculate the nuclear spin. So the further, it is going to further split to two orbitals, and this is called the splitting from the spin orbital effects. So how can we actually, if you have a look on this one, S is having only, it is not going to split into the two, only P, D, F, and G are going to be splitted into the two suborbitals, and these are the spin orbital effect. And actually here, how it is going to be splitted, this is the very basic simple formula. Here actually this is called the total angular momentum. J is the total angular momentum, and here it is like 7 by 2. 7 by 2 is the J, the value of J. How can we calculate the J? It is simple, the angular quantum number plus minus half. So let's move from the S. S is the uh, for S, it is only having the value of half. How? Because the value of angular momentum quantum number for S is 0. So 0 plus half uh, will remain half, and 0 minus half will remain half. So there is no differentiation between the both splitting. So we will be using only the plus one, because all these splitting are shown in the positive form. So let's move to the second. Let's go for the P. The P, the value of L, that is the angular quantum number for the P is 1. So 1 plus half will be 3 by 2, and 1 minus half will be 1 by 2. So first will come positive summation, and then the second will come the negative summation from the angular quantum number. So similarly, let's suppose for the D, the value of L for the D is 2. So 2 plus half will be 5 by 2, and 2 minus half will be 3 by 2. Or similarly, you can do for the rest of the other angular quantum number, and you can calculate the value of J, which is the uh, total angular momentum, or sometimes we call it the spin. We will explain in the next slides. So we have explained here what is the how to calculate the angular quantum number, and then the total quantum number, and then move to the multiplicities of the states. Actually, this describes the the maximum occupancy of these orbitals. Maximum occupancy means maximum capacity of holding neutron or proton separately in these orbitals. So the total will remain the same, like we calculate the total number of electrons in the subshells or the orbitals in electronic configuration. So the maximum capacity of the electron of the s orbital to hold the electron is 2, and maximum capacity of the p to hold the electron are 6. And this is similar to the I am just going to give you as a reference, so it will be easier for to remember. So the total capacity will remain the same as we have discussed, or you can use for the electronic configuration. So just I'm moving to here, how to calculate the multiplicity of the states, and this is the very simple formula. This is 2j plus 1, and j is the this one we have already calculated j by using this formula, and this is the total angular momentum, and sometimes it is called the spin, because this will be we will use to calculate the spin of the nuclei. So this is the 2j plus 1. Let's start from the s. S, the value of j is half. And so 2 multiplied by half will be 1, and 1 plus 1 will be equal to 2. So let's suppose for the p, this one p, this is the 2 multiplied by 3 by 2, 2 and 2 is going to cancel out, and then 3 plus 1 will be 4. And similarly for the half, 2 multiplied by half will be 1, and 1 plus 1 will be equal to 2. So similarly you can do for the rest of the these levels of the orbitals. So the important is the next important is like here it is indicated with the color lines or something. The number are written over here. These are called the magic number, and these are the similar to the like in electronic configuration we call it the shells, K shell, L shell, or the M shell. So, like here, how can we differentiate? I will explain in the next slides about the magic number. But here, just to show you how we are going to calculate the magic numbers. So here you can see the difference. The maximum capacity of S is 2, and this P will be 6. 4 will be on the four electron protons or the neutrons are filled up at P3 by 2, and 2 are filled up in P1 by 2. So total protons or the neutrons are 6. And this is the first energy gap. There is another energy gap, and this is another energy gap from D3 by 2 to F7 by 2. And here you can say there is another energy gap between the 7 by 2 and P3 by 2. There is another energy gap between the uh, G9 by 2 and G7 by 2. So actually the within the energy gap or before the energy gap, the total occupancy of the protons or the neutrons are called the magic number. And here for this is 2, and this is 6 plus 2 is 8 because there is an energy gap, and then energy gap is here. From here to this, there are total number of protons or neutrons are 20, and from here to this energy gap 28. So from here to here are the 50. So these are all about the energy level. So because this is very important to understand, because this knowledge we will be using to calculate the nuclear spin. So there is another diagram is written over the right hand side, and actually this is the excited state, the uh, building of the protons and the neutrons at the excited state, and this is the ground state energy levels. So somehow what is the main difference here? The first difference is here, the same energy levels are here, but in the excited state, S1 by 2 is in between D5 by 2 and 3 by 2, and here is above the D3 by 2. So this is the simple difference between the excited and the ground state, but we will be using this excited state to calculate the nuclear spin. So let's move to the another slide. This is the whole energy levels of the nuclear shells. So here we will discuss about the magic number and the pairing of the neutrons and the proton. So what is the importance of the magic number? So magic number actually when the shell is full, that is when the nucleons have used up all the possible sets of quantum number assignment, a nucleus of unusual stability forms. So when the shell is full, the nucleus will be the having the highest stability. So this concept is very similar to that which is found in an atom where a filled set of electron quantum numbers result in an atom with usual stability, like in case of the inert gas. So this magic number here is similar to what we are using the or defining the stability of the inert gas or the 8th A group. So there, so that when all the protons or the neutrons in a nucleus are in field shell, the number of protons and neutrons actually is called the magic number that we have discussed in the previous slide. So some of the magic number are here: 2, 8, 20, 28, 50, 82, and so on. So there are three possibilities. Let's suppose the nuclei maybe has the magic number of protons, like in case of the tin 116, and it is the atomic number of tin is 50. So tin is having the matching number with respect to the protons. Similarly, some nuclei having the magic number with respect to the neutrons, like in case of the iron atomic number is 26, and when you just subtract 54 minus 26, and there are the 28 neutrons. That means iron 2654 having the magic number of the neutrons. And the third possibility is when both number of protons and neutrons are in magic number. So like in case of the example of calcium, atomic number is 20, atomic mass number is 40. So both protons and neutrons are 20, 20 each. So that means calcium is having the both protons and neutrons are in magic number. So we call it the doubly magic. The magic number are indicated on the chart of the nuclides as well, as we have discussed in the previous slide. So here is the pairing. Actually, this is very important, and we can fill the number of protons and neutrons separately. So let's suppose, and it's similar to the electronic configuration. One is having the clockwise movement, other one is anti-clockwise, or we call it this is the up spin, this is the down spin. So first neutrons with the up spin, and second with the down spin. So clockwise, anti-clockwise cancel to each other. That means it doesn't have any nuclear spin. So similarly, we can do for the protons. So this is for the S, and for the P, there are the first P3 by 2, there are the possibility of 4 protons or the neutron. So first come up with this, second this, third up spin, 4 down spin. Again, they are paired and there will be no nuclear spin. So actually this is the pairing of the neutrons and the proton. And this formula you already know. Just for the simplicity I have mentioned over here, because you have to calculate the number of protons and neutrons in each step to calculate the nuclear spin. So simply this is the symbol of the nuclide, this is the atomic number, this is the mass number. So the number of neutron will be the mass number minus atomic number. You can calculate the number of neutrons. So first, let's move to the first case when even number of protons and even number of neutrons are present, and we have already discussed before when, because even both even number, so there will be no spin. The spin of the nucleus will be 0. Nuclear spin will be 0. So here proton, neutron, there are the same energy levels with respect to the protons and the same energy level with respect to the neutron. And the example here is, let's suppose the first example is carbon 612, 6 protons and 6 neutrons. And this is the building of the protons in the energy level, first with the up spin, and then the second will the down spin, third, fourth, fifth, sixth. So all the protons are filled up, And because there are two, maximum capacity to hold the number of protons of S is 2, and maximum capacity to hold the number of protons in P3 by 2 is 4, because this is the maximum capacity to hold the number of protons in this case, and same in this case of the number of neutrons. So you just have a look, number of protons, there is the same building of the protons as in case of the same uh, building of neutrons in the energy levels. So there is no unpaired spin. So that's why when there is even combination, the spin will be 0. So there is the filling of the protons or the neutron in the energy level, and you can write like in this way, similar to the electronic configuration. The two protons uh, are filled up in S1 by 2, 4 in 3 by 2, and similarly for the number of neutron, and the spin for this is 0. And there are the other cases like helium 24, oxygen 816, or the sulfur 32. You can calculate in a similar way. All three are having the even number of protons and the even number of neutrons, and the nuclear spin for these nuclei will be 0. So move to the second case. So second is the when even number of protons or odd number of neutrons are present, or vice versa. Vice versa mean if there is odd number of protons or even number of neutrons are present. Let's start with the example carbon 613, and this is the one you are using in the NMR. Carbon isotope 613 is active in NMR having the nuclear spin. So let's see how we are going to calculate the nuclear spin for the carbon 613. So again, the number of protons are 6 and the number of neutrons are the 7. So this is the simple representation, 2 and P holding 4, and this is the furthest into the individual orbitals. That means S half holding 2 and P3 by 2 is holding 4 number of protons, and similarly for the number of neutrons, and the seventh one neutron goes to the p half, and this you can have a look over this building up the protons in the energy level. So it is the first protons with the up spin, second protons with the down spin, and this one s is totally filled. Now the protons move to the p3 by 2, up spin, down spin, up spin, down spin. So protons are actually filled up. So there, because there are the maximum number of protons are the 6, and same filling of the neutrons is over here, but seventh neutrons move to the p1 by 2, because the maximum capacity for P3 by 2 is 4, and next we'll move to the P1 by 2. So now move to the nuclear spin. So there is no contribution of the protons towards the nuclear spin, because all the protons are the pair. But in case of the carbon 613, the neutron, one neutron is unpaired, and this will contribute to the nuclear spin. So as we have discussed before, this is the angular quantum number, and this is the total angular momentum. So, and I have said earlier, these are very important, because we will use to calculate the nuclear spin. So just have a look. This upspin neutrons is present in P1 by 2, and this is the nuclear spin of the carbon 13. So in which it is going to exist, that will be the nuclear spin of this neutron. So nuclear spin of carbon 613 will be half. So let's put for the similar case for the phosphorus 1531. This is also active in NMR, and the spin is half. It is having the 15 number of protons and 16 number of the neutrons. Similarly, you can fill up here the number of protons and the neutrons, and all these are filled up, and then one and this spin, because here protons are 15 and neutrons are 16. So all neutrons are filled up, that means paired, and the nuclear spin will be due to the number of protons, because number of protons are unpaired. So, and the 15 number of protons will move to the 2s orbitals. So if it is here, then the spin of the phosphorus 1531 will be half. Half is due to s 1 by 2, and that is the total momentum of the s, and that will be the spin of the phosphorus 1531 due to the presence of the protons in s half. So this is the another way to fill up the number of protons, like 2 are filled up in S1 by 2, 4 are filled up in 3 by 2, then 2 are filled up in 1, P1 by 2, and there are 6 are filled up in 5 by 2, because there is maximum capacity to hold the protons are 6, and then the next proton will move to the S1 by 2. So total there are 2, 6, 7, 8, 9, 10, 11, 12, 13, 14, and this will be the 15 number will move to the S2 as 1 by 2, and look at only this is going to contribute to the nuclear spin. And similar you can do for the other nuclide. Proton NMR, again only having the one proton, or one proton is present over here in S 1 by half. So the nuclear spin of the proton will be 1 by 2. And similar you can do for the oxygen 17. So let's move to the third case, when odd number of protons and odd number of neutrons are present. And this is the, we are going to apply in this case Nodin rule, and it is called the Nodin number. We will calculate this one by using very simple formula. And if the value of n is even, then what is the nuclear spin? So the case 3 is all about when there are both odd number of protons and odd number of neutrons, and n is even. The total number of n, Nodin number, is even, then how to calculate the nuclear spin? So the example is here, phosphorus 1532, total number of protons are 15, total number of neutrons are 17. So let's first look at the filling of the protons and the neutrons in the energy levels. So this is the proton. First comes with the upspin, downspin, second, third, fourth, fifth, sixth, seventh, 8, 9, 10, 11, 12, 13, 14, 15. So these are the total number of protons are 15. So total number of neutrons are 17. So 14 is 15 was up to here. So this is 16 and this is 17. 17 neutrons will be present at D 3 by 2. So both are going to contribute, because both protons and neutrons are odd in number, and so both neutron and protons contribute towards the nuclear spin. So now it is complicated that how can we calculate the nuclear spin, because both are having the spin. So that's why we are going to apply the Norden rule. And look at, this is the similar way to actually with reference to the energy levels. And one unpaired in case of the proton is present in S1 by 2, and neutron, one unpaired is present in D 3 by 2. So this is the Nodin number. You calculate the Nodin number by using this formula. And this is the J. J is the total angular momentum, and L is the angular quantum number, in which unpaired protons and neutrons are present. So this is very important. So we will just look at the last protons or the neutrons, or the unpaired protons or the neutron. So like in this case, how I'm going to calculate the number of J and L. Let's suppose this is the J1. J1 is the total angular momentum, and this is for the proton. J1 proton is here, and this is the 1 by 2 because it is present in S 1 by 2. So that's why the total angular momentum for this proton is 1 by 2. So this is 1 by 2. So for J2, for the neutron, this unpaired neutron is present in 3 by 2. So the value of J is 3 by 2. Now move to the angular quantum number L1. L1 for the proton. So it is present in the S, and the value of L for the S subshell is 0, and the value of now move to the neutron. It is present in the D subshell. The value of L for D is 2. So this is the actually the values for the J and L from these energy level. So if you sum up will give you the even number. So that is the case number 3, when both protons and neutrons are odd in number and the n is even in number. Then how to calculate the nuclear spin? So just you have to subtract the lower value from the minus value from the total angular momentum from the light source, which is J2 minus J1. So here we have already calculated J2 is 3 by 2, J1 is 1 by 2, 3 by 2 minus 1 by 2 will be equal to 1. So this is the nuclear spin for the phosphorus 1532. So this is the third case. So you can do in a similar with the rest of the nuclei to calculate the nuclear spin. So move to the fourth case. So this is similar to the third case. It is also having a odd number of protons and odd number of neutrons, and Nodine number is also odd. In the previous case, this n number was even. So the difference is here, the n is present in the odd form. So let's again have a look on this example. This is the aluminum 1326. So number of protons are 13, number of neutrons are also 13. Both are the odd number. And just have a look on the building of protons. First proton with the up spin, down, second proton with the down spin, second, third, fourth, fifth, sixth, seventh, eighth, 9, 10, 11, 12, and 13. So this is having the 13th proton is unpaired. All the other protons are paired and similar because same number of protons and the neutron. The 13th neutron is unpaired and the rest of the neutrons are paired. So only this proton and this neutron contribute to the nuclear spin. Or in other way, you can say that both protons and neutrons contributes toward the nuclear spin. So how can we calculate the nuclear spin in this case? Again, up to this one is the same. You have to calculate the Nodine number, and this is the J1 plus J2 plus L1 plus L2, L for the proton, neutron. So J1 for the, let's go for the proton, and this unpaired is present in the D 3 by 2, and the value of J is 5 by 2. Sorry, it is present in D 5 by 2, and the value of J is 5 by 2. So I have written here the value of J1 is 5 by 2. And in a similar case, the neutron, unpaired neutron is also present in D 5 by 2. And the value of J for this neutron is also 5 by 2. Now calculate the angular quantum number. So L1, because this unpaired proton is present in D and the value of L for D is 2. And similarly, in this case, for the neutrons, the value of D is 2. So when you sum up all these, the net value will be 9. So this is odd in number. So this is different from the previous case. So when n is odd, then how you can calculate the spin. So you just have to add up the J1 plus J2. So in this case, we have already calculated J1 is also 5 by 2 and J2 is also 5 by 2, and sum up will give you the value of 5. So the nuclear spin for the aluminum 1326 is 5. And you can do for the rest of the nuclide, like the example is given here. So the main important thing is when both protons and the neutrons are present in odd number, the nuclear spin will be the integer. That means 1, 2, 3, 4, 5, and so on. So these are the building up protons and the neutrons in the energy levels, and you can also write in a simple nuclear configuration by using the same energy level into the horizontal form as P 3 by 2, P 1 by 2, D 5 by 2, and so on. So this is all about the nuclear spin. There are 4 cases in this presentation I have discussed, and by using these 4 cases you can calculate the nuclear spin of the any nuclide. However, this is important to note that there are few exceptions are available, and because this is beyond the general knowledge, and maybe we will discuss in the future lectures. So this is the periodic table mentioning the nuclear spins, which are also active or undergo NMR, and and the values are ranging from half to maximum 8. And you can, like here, it is the red is for the carbon. These are just the atomic number are given. That means carbon 613 is having the spin of half. Similarly for this, it is having the spin of half. And there are few exceptions, so I'm not going to discuss here. So in a general way, you will be efficient to calculate the nuclear spin based on the filling of the protons and the neutrons. So this is all the nuclear shell model. So thank you very much for listening or watching this video. Hope to see you in the future lecture. So at the end, I'm going to just mention the reference. These are the 2 references of our own book. And again, thankful to my teacher, supervisor, mentor, Professor Iftikhar Imam Naqvi, to give us knowledge. So we are now able to transform this knowledge to the other generation. So also some of the data are taken from the nuclear physics from Kaplan. Thank you very much.